Okay, we're going to be spending 2 days on section 3.3. The topic is increasing, decreasing in the first derivative test. And first statement is that the derivative is related to the slope of a function. We always read functions from left to right. And as you read, if your function is going down, slopes of the tangent lines will be negative, and the first derivative will also be negative. If your function is going up, as you read from left to right, slope of the tangent lines will always be positive, and the first derivative will always be positive. What that means is if you see a sign change in the slope, there's going to be an extrema. These pictures do the best job of explaining. Here I have a function that's decreasing. The first derivative is negative. The slope of the tangent line is negative. When the function switches to increasing, now the tangent lines have positive slopes, so the first derivative is positive. The point where the function switches from decreasing to increasing is a minimum, and in terms of derivatives, if the first derivative switches from negative to positive, you know you've found the location where the function has a minimum. If the change in sign of slopes goes from positive to negative, you'll have a maximum. If the first derivative is positive, then the first derivative becomes negative. The point where that occurs is a maximum. These point C's are called critical points. You can have a first derivative equal to 0 or not exist, but if the sign doesn't change, you will not have a maximum or a minimum. So the first derivative equal to 0 at this C value, but a positive slope and a positive slope does not produce a minimum or a maximum. Okay, next we're going to look at some examples where we'll find minimums or maximums without having to graph the function. Okay, for this example 1, identify the open intervals on which f of x equals x minus 2 cosine x is increasing or decreasing. And again, what we'd like to do is be able to figure out these intervals without plotting it. So steps 1 and 2 are take the derivative, set it equal to 0, and find the critical points. Before I reveal the answer, try and do that on your own. Find all critical points for the function. Okay, if you solve correctly, you should have gotten sine x is negative 1/2. Where does the y coordinate equal negative 1/2? It's 7 pi over 6 and 11 pi over 6. So I plotted those. And instead of going forward, I went backwards. We know that sine is a period of 2 pi. So if I subtract 2 pi from each of these, 7 pi over 6 minus 2 pi is a negative 5 pi over 6. And 11 pi over 6 minus 2 pi is negative pi over 6. And 0 is just a reference point on the number line. So now that we have our critical values, what we're going to do is pick numbers to test in each of these intervals. So numbers that I want to test is between negative pi over 6 and 7 pi over 6. 0 is a good number to test, so I'm going to put an x there. Between 7 pi over 6 and 11 pi over 6, which is down here, I think this point here would be good, so I'm going to test 3 pi over 2. Past 11 pi over 6, a nice easy trig point is 2 pi. And then going backwards, again, between negative pi over 6 and negative 5 pi over 6, a good point to test would be negative pi over 2. And those are my test points. Okay, now that we have test points, we'd like to determine what happens to the first derivative in that entire interval using that test point. So I'm going to start with the test point of 0. I'm going to plug that into the first derivative. F prime of 0 is 1 plus 2 sine 0. The sine of 0 is 0. 2 times 0 is 0, and we get f prime of 0 equals 1. While the number is maybe kind of important, what's far more important is the sign. This 1 is positive. So over on my number line here, I'm going to say that f prime of 0 produced a positive first derivative, which means the function is increasing. Okay? Doing one more, if I wanted to try 3 pi over 2, 1 plus 2 times the sine of 3 pi over 2. The sine of 3 pi over 2 is over here on the unit circle. That y coordinate is negative 1. So now we have 1 plus 2 times negative 1, which is negative 1, and we get a negative value. So the test point of 3 pi over 2, the first derivative is negative, which means the function is decreasing. And what we've just discovered is because the derivative changes from positive to negative, the function is going from increasing to decreasing. So we know that at 7 pi over 6, we have a maximum. Okay? I need you to do the other two test points that are on the screen. You're going to test 2 pi, figure out if the function is positive or negative. Figure out if the derivative is positive or negative. See if the function is increasing or decreasing. Test negative pi over 2. Figure out if the derivative is negative or positive. Find out if the function is increasing or decreasing. And then determine what happens at these 1, 2, 3 other points and write intervals for increasing and decreasing. I'll have the answers up in a minute. Okay, here come the answers. Negative pi over 2 is the same thing as a positive 3 pi over 2. So when I plug that into the first derivative, I'm going to again get a negative first derivative, which means the function is decreasing. And then 2 pi is the same kind of an output as 0, because 0 and 2 pi are the same thing on the unit circle. So this is going to produce a positive first derivative, which means the function is increasing. So my overall results for all these critical values is decreasing to increasing at negative pi over 6 produces a minimum. Decreasing to increasing at 11 pi over 6 also produces a minimum. So what's happening is we're alternating back and forth between decreasing and increasing at all the critical points. So the final answer written in interval notation is that we will have an increasing function from negative pi over 6 to 7 pi over 6, and then from 11 pi over 6 to 19 pi over 6, and I'm sorry for writing over my own writing, and then decreasing is negative 5 pi over 6, negative pi over 6, with 7 pi over 6 to 11 pi over 6. And because this is a trig function, those will just keep repeating at certain intervals. Okay. So I don't think anybody's going to master increasing and decreasing after just one example. The second example on the right, same kind of a process, but does not involve trig, so maybe the algebra will be a little bit easier. It says for the function below, find the critical numbers, find the open intervals in which the function is increasing or decreasing, apply the first derivative test to identify relative extrema, use your calculator to confirm your results, and make a sketch. The reason for the really long instructions is that I believe that that's the same way your homework is worded, so it's just an example of how they're going to ask you this type of question in your homework. So for part A, take the derivative and find the critical numbers, pause the video, get your answers first before I reveal them. Okay, a whole lot less algebra in this question. Hopefully you got your first derivative to be 4/5 x to the negative 1/5, which is written as a fraction this way. Setting that function equal to 0 will have no solutions, but there is a critical number at x equals 0 because critical numbers occur when the first derivative equals 0 or when the first derivative is undefined, and we cannot use 0 as an input into that first derivative function. So my only critical value is at 0. Test points left of that negative 1 and right of that positive 1 are both easy numbers to work with. If I take negative 1, plug it in the derivative, I'm going to get a negative output. If I take positive 1, plug it in the derivative, I'm going to get a positive output. So that implies, or that tells me, that the function is decreasing and then increasing, so 0 will be a minimum. Decreasing from negative infinity to 0, increasing from 0 to infinity. And to answer the third question, since the first derivative changes from negative to positive at x equals 0, f of x has a relative minimum at x equals 0. The minimum is 1. Now this is an extremely important point right here, because the graders for your AP test will remove points from your score if you're not very careful about answering a minimum or maximum question. Minimum is always the y value. It is not an ordered pair, and it is not a point. Okay, minimum needs the y value. When they say what is the minimum of the function, you must report the y value. You can say that it occurs at whatever the x value is, but if they ask for a minimum or a maximum, only report the y value. The next screen will show graphs of these two functions just to confirm that what we've done is correct. So here are the two functions. The first function that we graphed was f of x equals x minus 2 cosine x. And what's kind of interesting about that is that f of x equals x would be just a straight a straight 45-degree line going up. But if I subtract 2 cosine x, cosine oscillates up and down, you get a line or a function that goes up from left to right, but it goes in an oscillating pattern. Notice that there are several cases where the function switches from increasing to decreasing. Here's a maximum, here's a minimum, here's a maximum, here's a minimum. And again, I used Desmos to plot that function and clicked on a point which gave me the ordered pairs. Those ordered pairs match what we found in the previous screen. And then the second one, you can see what the function looks like. It is a continuous function that has a point that does not have a derivative. Again, the slope of the tangent lines are negative, the slope of the tangent lines are positive, and there's a negative here. So we found a negative on a function even though the derivative doesn't exist at that x equals 0 point. And 1 is highlighted because that is the minimum. Okay, 2 more examples for you to try. There's no new instruction in these parts, just 2 more functions. The one on the left is very similar to the one that we just did. So take the first derivative, find the critical points, set up your number line, test your regions, and figure out whether or not there's a minimum or maximum. And the one on the right's a little bit trickier because there's an absolute value here. And as a reminder, you can take an absolute value function and split it into 2 other functions depending on whether your the material inside the absolute value bars is positive or negative. So a hint for each of those. Answers will come up in about 15 seconds. Okay, first answer. First derivative is this. Written in fraction form, you get this. There is a critical number at x equals 1. Okay, the first derivative does not exist when x equals 1, so take 1, put it on a number line. Good points to test would be 0 and 2. Notice that the number line is pretty well organized and labeled. You have to have these labels on here. The first derivative, when I plug 0 in, the first derivative is positive. And then when I plug 2 in, that is also positive. The reason why they're positive is because the exponent in the denominator has a even power. Oops, let's not do that. Let's not obliterate it. Let's highlight it. The exponent has an even power, so that 2 there causes the denominator to always be positive, which makes all the outputs on the number line to be positive no matter whether I test left or right of the critical value. Anyway, the function, because both derivatives were positive, the function is always increasing, so we have a situation where the function is going to go up. First derivative doesn't exist, and then it's going to go up again, and you'll see a picture of that in a second. But there is no max or min, and the function is always positive on the function is always positive. Try the second example. So if we take our function and realize that there's going to be a turning point at 2, absolute value functions look like v's. At 2, I'm going to test what happens to the right of 2 and to the left of 2. If I pick numbers bigger than 2, I'm at the top branch of the absolute value definition, so I'm just going to rewrite the function, take the derivative, and get the derivative equals -1. If I pick numbers less than 2, the material inside the absolute value bars is negative, which means now I need to take the opposite of that negative quantity. So the function changes into this, and when I take the derivative, I get +1. I know that the function derivative does not exist at 2, so that's my only critical point. Setting the first derivative equal to 0 doesn't make any sense because there's no variables, so 2 is the only critical point, and I know that left of 2, it's always increasing. Right of 2, it's always decreasing. So now I know that increasing -infinity to 2, decreasing from 2 to infinity. And written in very small print here, it says since f prime changes from positive to negative at x equals 2, there is a minimum value of 3 by the first derivative test. So the support is the number line, well labeled. The answer must cite the change in sign for the derivative and the first derivative test. And then the next screen will show you the graphs of these 2 functions. And here are the plots. So the one we just did, the absolute value function, it does indeed have a maximum of 3 when x equals 2. And then the first one, this is what it looks like if you have an increasing, an undefined derivative, and then increasing again. So at this point here, which I tried to expand, the slope of a vertical line does not exist. So this function increases, undefined derivative or undefined slope, and then increases again. Okay, that's it. That's the first day of section 3.3. The second day is a lot shorter.